This is experiment 15, chemical equilibrium and Le Chatelier's principle. Le Chatelier's principle states that if a stress is applied to an equilibrated system, the system will adjust itself to reduce the impact of the stress to the system. All right, a so-called stress is a change in condition. A change in condition that can disturb the equilibrium. We call it a stress. Okay, there are many changes that can disturb an equilibrium. Okay, such as adding or removing a component from the system, change in pressure, change in reaction system volume, change in temperature. Okay, all of those changes can affect the position of an equilibrium. In this lab, we focus on two things. Number one is the concentration change, a change in concentration of a component in the reaction system, okay, be it adding or removing a component from the system. Another change we're going to test is the temperature change. Okay? Now first, let's talk about the concentration change. We do a concentration change by adding or removing a component from the system. Okay, I put a generic equilibrium on the paper here. Okay, assume there's a system where reactants and the products are in an equilibrium. Now, Le Chatelier's principle says that. Le Chatelier's principle states that if you add a component to the system is going to move to the direction so that the added component is consumed. Therefore, addition of a component in the reactant side or removal of a component in the product side, the equilibrium will shift to the right to consume the reactant added or to produce the product removed. Okay. Similarly, removal of a component in the reactant side or addition of a component in the product side, the equilibrium will shift to the left. We are going to run a few reactions to test about the concentration change, the impact of a concentration change to an equilibrium. The first one is about this reaction. Okay, copper 2 plus ion, copper 2 plus ion in water, it will combine with 4 water molecules to form a copper-water complex. So copper 2 ion react with ammonia molecules in the water solution. The ammonia will replace the water out from copper, combine with copper to form a copper-ammonia complex and to produce water. On the left, the copper 2 ion complex with water shows a pale blue color. This is a copper 2 ion solution, copper 2 sulfate. You can see the pale blue color. It is from the complex between copper 2 ion and the water molecules. On the right side of the equilibrium, the complex between copper 2 ion and ammonia molecules gives a dark blue color. So if we perform this reaction, we can predict how a change can affect the direction of the reaction by observing the change in the color of the system. So what do we do in this part of the experiment? We're going to take a copper 2 sulfate solution, which means we have copper 2 ion complex with water. Then we'll add ammonia to it, and we'll try to observe the color change. Once we're done with that, we're going to add HCl to the reaction mixture. What does HCl do? HCl looks like has nothing to do with the equilibrium listed above. Well, HCl contains hydrogen ion. Hydrogen ion can combine with ammonia in the water solution to produce ammonium ion, which means when you add HCl, you are taking one reactant in the above equilibrium, the ammonium. You're taking ammonium away from the original reaction system. Like we said earlier, if you remove something, the reaction is going to shift. So based on what we learned from the Chatelier principle, when you take ammonium away, the equilibrium is going to shift to the left. The dark blue color will disappear. It will become pale blue again. So that's what we're going to do in this lab. We're ready to start. Now before that, I would like to remind everyone that the report sheet of this lab is different from the report sheet in the lab manual. Please follow the video, follow the procedure, and fill in your report sheet provided on the canvas. Okay? So this is what we need for this part of the experiment. We need a copper 2 sulfate solution, pale blue color. We need an ammonium solution. We need a hydrochloric acid solution. So first, we will add about a ml of copper 2 sulfate to a test tube and observe its color. 1 ml is about 20 drops. Okay, that's the color. We call it pale blue. Make sure you take a record of the color on your report sheet. Now we'll add ammonia to the test tube to observe the color change. We'll keep adding the ammonium until the color becomes dark blue, and we'll count how many drops are added. 1, 2, 3. Oh, there's a color change. Let me shake it. Well, it changed a little bit. Not dark blue yet. We'll keep adding. We got 3 drops already. 4, 5, 6, 7, 8, 9. It's getting darker. 10, 11. We'll keep adding until 1 more drop, the color doesn't change anymore. 12, 13. Well, about 13 drops. Okay, let me add 1 more to see if it changes. 14, the same. Okay, 14 drops. Okay, either 13 or 14, but let's say 14. 14 drops, the color changed to dark blue. Okay, record the color and the drops of ammonia added on your report sheet. Now, we're gonna add, well, before we add anything, on the lab report, it asks you to predict how the equilibrium shifted when the ammonia is added. The equilibrium we're talking about is the one I just showed you guys, okay? The copper with ammonia, that equilibrium. It is also in your lab manual, okay? You just answer whether it's shifted to the left or to the right. Okay, now we're gonna add dropwise hydrochloric acid to the test tube. We'll keep adding it until the color goes back to the original pale blue color. And we'll take a record of how many drops of hydrochloric acid needed. One, 2, 3, 4, 5, okay. 5, 6, 7, 8. It is almost the reverse of the process of adding ammonia. Thirteen. 14. Okay. It goes right back to the original color. Clear. 14 drops. 14 drops of ammonia at the beginning. Now we added 14 drops of hydrochloric acid. You record this on your report sheet and answer the question about the equilibrium. The second experiment about the concentration change is about this equilibrium, an equilibrium between dihydrogen phosphate and hydrogen phosphate in water solution. This experiment needs to use litmus paper again. Okay, so these are the litmus papers. We have red ones and blue ones. We have used them before. We know that a blue litmus paper will turn to red if it's get into contact with an acidic solution. A basic solution will make the red litmus paper changes to blue. Well, sometimes there will be solutions where neither paper will change color, or both papers, both the red one and the blue ones, may change a little bit, but not as significant as what you will see for acidic or basic solution. Then we claim this kind of solution, we claim it is close to neutral. In this lab, we'll just say it is neutral. Okay, so this is what we're going to do. First, we're going to take a solution of a mixture of dihydrogen phosphate and hydrogen phosphate and test its acidity, basicity with litmus papers. Then we'll test the acidity or basicity of our 1 molarity hydrochloric acid. Well, we know hydrochloric acid solution is an acidic solution. So ideally, we're going to observe the blue paper changes to red. We're going to do that. Then we are going to add the hydrochloric acid solution to the mixture of the phosphate solution. Okay, we're adding an acid to it. Then we will test it again with the litmus paper. This time, we will observe how the litmus paper will change color after adding acidic solution to the original mixture. After that, you have to predict how the equilibrium shifted after the acid is added. Okay? So let's go into the experiment. This is the mixture of phosphate, hydrogen phosphate solution, dihydrogen phosphate and hydrogen phosphate. Okay. I'm going to take about 2 milliliter added to the test tube. Okay, I'm going to test this solution with red and blue litmus paper. I'm going to dip the glass rod into the solution, bring out a drop of solution, put it on the red paper. Well, it kind of darkened a little bit. It didn't change total blue, but it's kind of purple-ish. It changed a little bit. I'm going to rinse my glass rod with distilled water. I'm going to test the pH, the solution with the blue paper now. Wow, it changed a little bit too. I would say it's purplish again. So both blue and red papers changed a little bit, but not significant. Well, you may want to ask, what do you mean by saying not significant? Later on, when we test this with a real acidic solution, you're going to see the color change. What does change to red mean? Right now, this is the color. Okay? So when you record this observation, you can write down color changed a little bit. I'm going to keep these 2 pieces of papers here so we can do a comparison later on with other papers. Now, let's test the litmus paper with a true acid, hydrochloric acid. A drop of acid on the red paper. Well, didn't change too much, didn't change at all. On the blue paper, now you see the red color here. Blue changed to red. Compare the blue paper we just did with the phosphate mixture. Now you see the difference. Compare the phosphate with a true acid, this barely changed at all. So based on our observation right now, we can conclude the phosphate mixture is close to neutral. The hydrochloric acid is acidic. Okay, now this is the original mixture of dihydrogen phosphate and hydrogen phosphate. We tested it with the litmus papers. We concluded that it is close to neutral. We also tested the hydrochloric acid with litmus papers, and we concluded it is very acidic. So now this is what I'm going to do. I'm going to add a drop of this acid into this mixture, and we will test the pH. Now we're going to test the solution with litmus papers again. So when we add hydrochloric acid, we know we are adding something acidic to it. Just going to add 1 drop. We're adding something acidic to it. Okay, before we test the solution with the litmus paper, we would think, okay, if you add something acidic to it, the solution will become acidic. Then the blue paper will turn red. Let's see if that is the case. Burn a drop on the red paper. Same as before, changed a little bit, but not too much. On the blue paper, this is what we were thinking that, oh, it might change to red this time because we added acid to it. Look at it. Oh, it changed a little bit. Well, compare what a change an acid will cause to the blue paper. This is not changing. It changed a little bit, not too much. Based on this observation, basically these two, what we see, the paper color change is the same as the ones we had earlier. Okay? Both papers changed a little bit, but not very significant, which means adding acid, HCl, to this solution didn't cause the change in the acidity. Why is that? Okay, this is the equilibrium we were talking about. Okay. What makes the blue paper change to red is the hydronium ion, which is the product here. When you add hydrochloric acid, to a solution, you're adding this one. When you add this one, hydronium ion, it will change the blue paper to red. But in this case, the color didn't change. What happened? Well, look at this equilibrium. If you add a product, the equilibrium is going to shift to the left to consume that product. The amount of the hydronium ion added are consumed by this equilibrium when it goes to the left. As a result, the solution didn't become acidic. Take a record of all of this and your explanation on the report sheet. The third experiment about concentration change is about this equilibrium. An equilibrium between iron 3 plus ion and iron 3 thiocyanate ion. On the left, iron 3 plus is yellow. On the right, iron 3 thiocyanate ion is red. So what we're going to do for this equilibrium, this is what we will do. We will first mix a mixture. We'll first make a mixture of the two ions, And then we will either add iron 3 plus ion to it, or to add thiocyanate ion to it, and observe how the color will change from the original mixture, and predict how the equilibrium has shifted after you add either one of those. Did it shift to the left? If it shifts to the left, the solution will become more yellow, or you say the red color may fade. If it shifts to the right, the solution may become darker in red. Okay? After these two experiments, we're going to do a third one. We're going to add a lot of chloride ions to it and observe the color change and predict the shift of the equilibrium. Well, in this equilibrium, there's no chloride ion at all. Why does adding chloride ion change the color of the solution? Well, this is what happened. Although inside that equilibrium, there's no chloride ions at all, but when you have a lot of chloride ions in the system, chloride ions will combine with iron 3 plus ion. Okay? Basically, by adding lots of chloride ions, you are removing iron 3 plus ions from the system. So you're removing this ion you're taking it away from the system. Okay, then you observe the color change, you predict how the equilibrium will shift. Now let's start making the mixture of iron 3 plus and the thiocyanate ion. Okay, we need 50 milliliters of distilled water. We need 1 ml of the iron 3 chloride solution and 1 ml of the potassium thiocyanate solution. This is the 1 ml of the iron 3 chloride. See the yellow color, iron 3 plus in water. So I'm going to add it to the distilled water. I'm also going to add 1 ml of the potassium thiocyanate solution. Look at that. Okay, that is the color of the mixture of iron 3 plus and thiocyanate ions. Now I have transferred 2 ml of this to each of the 4 test tubes. Okay, one of these test tube number 1, I'm gonna leave it there to use it as a control, as a standard. The other 3 test tubes, I'm going to perform some reactions, and then we'll see how each reaction will change the color of the solution. We're going to use the color change of this solution compared with the control that we have. Okay? Okay, please take a record of the color of this solution right now. Okay, I will call it a reddish brown color, Okay, we're gonna leave this test tube here, let it serve as a control. Okay, we're gonna perform reactions on these 3 test tubes. This is test tube number 2. And we're going to add 10 drops of iron 3 chloride to it to see how the color will change. Notice the yellow color of the iron 3 chloride. I'm going to add 10 drops. 1, 2, 3, 4, 5. 6, 7, 8, 9, 10. Look at the color change. Wow, let's compare. This is the test tube after we add iron 3 chloride. This is the original control. I don't know if you guys can notice the difference. This one, to me right now in front of me, this one becomes a lot darker than this. So after adding iron 3 chloride, the solution becomes darker red. Okay, you take a record of this color change on your report sheet and predict how adding iron 3 chloride has shifted the equilibrium. To test tube number 3, we're going to add 10 drops of the potassium thiocyanate. One, 2, 3, 4, 5. 6, 7, 8, 9, 10. Wow, this one is even more obvious than the last one. Original control after adding potassium thiocyanate. Darker red again. Okay, take a record of the color on your report sheet and predict how the equilibrium has shifted. Test tube number 4. We'll add 5 drops of saturated sodium chloride. One, 2, 3, 4, 5. Well, we don't even need to look at the control anymore. We know the reddish brown color has faded. Okay? So take a record of this on your report sheet and predict how does adding sodium chloride has shifted the equilibrium. The next part of the experiment is about the temperature change. How will the change in temperature impact the equilibrium? Okay, many chemical reactions involve energy. Okay, one way to provide energy or taking energy away is by heating or cooling the reaction system. Okay. Reaction can either absorb heat or releases heat or energy. Okay. For a reaction that needs energy to react, we call that kind of reaction endothermic. For endothermic reaction, we can consider energy is a part of the reactant. Okay, energy is required for the reaction to go on. An exothermic reaction is a reaction where energy is released, okay, or produced. We can kind of consider energy as a product of the reaction. Therefore, if energy is provided to an equilibrium system, okay, it looks like you're adding the reactant for an endothermic reaction. Okay? As a result, if you add energy to an endothermic reaction, the reaction is going to shift to the right. For the same reason, if you add energy to an exothermic reaction, basically you are adding a product to the system. The equilibrium is going to shift to the left. This is the reaction we're going to perform in this part of the experiment. First, we're going to take a solution of the cobalt with water complex. We'll keep adding hydrochloric acid to it. When you add hydrochloric acid, you're adding chloride ions into the system. Okay? As a result, the equilibrium is going to shift to the right. The color will change from the pale rose. We're going to take a look at those colors later on. The color of the solution will change from pale rose to a deeper strawberry. Okay? So we're going to add hydrochloric acid to the solution until we observe the color change and predict how the equilibrium is shifted by addition of hydrochloric acid. Okay, we're going to do a second experiment, again to the original pale rose colored cobalt water complex solution. We're going to put it into a boiling water bath. I have a boiling water bath set up already. Okay. We're going to put it into a boiling water bath and observe the color change. Did it shift to the right, become darker, or did it shift to the left, become lighter? By doing that, we're going to predict whether the reaction is endothermic or exothermic. Remember, when we put the reaction system into a water bath, we are providing energy to it. Okay? So energy in this case may be in the reactant side, maybe in the product side. However, when you add energy to it, the equilibrium is going to shift away from that direction. Okay? From the color change, you know to which direction is shifted. And the energy will be on the other side of the equilibrium. That will tell you whether the reaction is endothermic or exothermic. You have to make a prediction on that based on your observation. All right, the procedure asks us to add 5 drops of cobalt 2 chloride to a test tube. I didn't add 5 drops. I added about 15 drops to hoping that we can observe the color change a little easier. Okay? Then we're gonna add, I made 2 of these. One of them, I'm gonna leave it as a control. So remember, this is the so-called pale rose color, okay? You can call it pale rose. You can call it any color you want. I see it a little bit pink, okay? So however you call it. And now I'm gonna add concentrated hydrochloric acid to it until we observe the color change. 1, 2, 3. Okay. 4, 5, 6. Oh, it darkened. It darkened clearly. Okay, I don't know if you guys can see that, but it's darkened a little bit. Well, let's add a little more. Seven, 8. That's one more. 9, 10. Wow, look at that. The color is very different. Okay, so the color becomes darker. The lab manual says this is darker strawberry. Okay, however you call it, but it is darker. The color becomes darker. Okay, you take a record of the color after the addition of hydrochloric acid and predict how the equilibrium has shifted. Now, I made another sample of the cobalt 2 chloride. Okay, I'm gonna leave it in the boiling water bath. Okay, the sample has been here for about 8 minutes-ish. So let's take a look of the color. Oh, it's hard to see whether the color changed or not. Okay, let's compare with our control. This is our control. This is the final solution. It clearly, to me, it becomes darker. Not as dark as the one that was added with hydrochloric acid, but clearly it is darker than the original solution. Okay, take a record of it and predict to which direction the equilibrium has shifted and predict whether the reaction you believe is endothermic or exothermic. Remember, adding energy darkens the mixture. Adding energy darkens the mixture. Based on that, you can predict the direction of the equilibrium has shifted. Again, remember, the equilibrium will shift away from the added component, in this case, energy. Okay, predict whether it is endothermic or exothermic. All right, that's all for today.